Now looking at quiz problems, first problem asked for the average velocity if something travels 100 centimeters in 4 seconds. And you get 100 centimeters divided by 4 seconds, and that's going to be 25 centimeters divided by seconds. If you didn't write out your units, and actually I'm not sure, these might have been domino lengths and cycles, whatever the units of distance are, whatever the unit of time is, that's the units that should go here. Using centimeters and seconds, I get 25 centimeters per second, meaning that on the average, the object in every second moves an average of 25 centimeters. Now, some seconds it might move further, and some seconds it might move less. If it's speeding up or slowing down, it's probably not going to move the same distance in every second. But when you average those distances over all the seconds, that's what you get. Okay, the main thing here, everybody pretty much got this, except some people didn't write the units, and you've always got to write the units with every problem. Okay, with every calculation. If a quantity has units, it always needs to be expressed by the units. On the second problem, you were asked to show your graph of number of dominoes versus length, or pendulum count versus length. And really all I was looking for was graphs that represent the general trend. As I commented in class, especially in the pendulum count, people didn't count their pendulums with the accuracy that would result in good graphs. When you're counting 100 or 200 cycles, it's easy to get distracted, and it seems like a lot of people did just looking at the data. We'll refine that. We'll see what the counts should have been. Okay, well anyhow, the number of dominoes that you can support at given lengths increases with the length. The longer the rubber band is, the more force it exerts, the more dominoes it can support. The graph should start somewhere out here, not at the origin, but it should be then increasing as you move to the right. Could be increasing in a straight line. I'd find that perfectly acceptable. A lot of times a rubber band is going to give you a curve that looks something like this. But in taking only a few readings, you could get a curve that looks like this, whether that's really what happened or not. So sometimes the straight line model, when you only have a limited amount of data, might be your best bet. But in fact, a lot of rubber bands will have this characteristic. Okay, pendulum count versus length. The longer the pendulum, the fewer cycles you're going to count. And the graph is going to look something like this. Now, I asked you to show me what your graph looked like. The counts were pretty inaccurate. Now, they did tend to decrease as the length of the pendulum increased. So they did have that characteristic, but they might not have had this kind of curvature. They might have even done this thing, kind of dive bombing toward the horizontal axis, which, if you think about it, would not be what you would expect. Okay? Or, you know, a straight line, or, you know, you could just get just about anything if you didn't count very accurately. And as I say, I think a lot of people didn't count very accurately. That's not what we were trying to measure. I just wanted to see what your graph looked like. So as long as the graph here is kind of decreasing, as long as the graph here is increasing and starting from some point, not the origin, I would consider that a perfectly good representation at this point. We can refine that later. Okay, third problem. We said the velocity of some object increases from 6 meters per second to 12 meters per second, and I asked for the average velocity. Now, some people thought a little bit too hard about this. This is a velocity, and this is a velocity. This is the minimum velocity, this is the maximum velocity. The average velocity is going to be between the minimum and the maximum. Okay, well, specifically, the average velocity is going to be halfway between the initial and final, assuming we have a linear v versus t graph. In other words, a uniform rate at which velocity changes, which is a completely different thing. So to get the average velocity, given the two velocities, the initial and final, we just average the initial and final velocities, and we get something like this. Okay, we get 9 meters per second. Now, a lot of people, maybe even a majority of the class, but a significant minority in any case, chose to subtract these quantities and then even sometimes to divide that by the 3, because you had a 3-second time interval. And as I said in class, that's not a totally bad thing to have done, but it doesn't answer the question that was asked. It was kind of along the lines of the calculation that I show you here, which was not part of the quiz. But since a lot of people moved along these lines, we need to look at this, okay? So, now, if you apply the rate of change definition to these things, you can get, and since you were given that it takes 3 seconds to go from here to here, that information would not have been used to find the average velocity, but if you felt like you had to use that 3 seconds, again, another motivation for what a lot of you did. Okay, this is the average velocity, plain and simple, but if you take the change in the velocity and divide by the length of time it takes, which would be the change in clock time, you get the rate of change of velocity with respect to clock time. It's not what was asked for, but you're on line, you're moving in the direction of this rate of change calculation, so I chose to address this at this point. So, from 6 to 12 meters per second, the change in clock time is, the change in velocity is 6 meters per second. The change in clock time was given as 3 seconds. So if you divide the 6 meters per second change in velocity by the 3-second change in clock time, you're getting the average rate of change of velocity with respect to clock time. And that calculation then, 6 divided by 3 gives you 2, and you have meters per second divided by seconds. Now, people wanted to say, well, that gives you meters. Well, no, it doesn't. If you multiply meters over seconds by seconds, you get meters. If you divide meters over seconds by seconds, you don't get meters. So you have to be careful, and you have to know what the rules are for working with fractions. And as I explained, that's going to be very prominently addressed in the documents that I ask you to work through for class a week from today. Okay? So, how do we do this? We have the two. We got meters per second divided by seconds. I wrote it this way as an intermediate step because then if you divide by seconds, that's the same as multiplying by reciprocal seconds. So we're going to multiply meters per second, which we represent as meters over seconds, times reciprocal seconds. Then when we multiply these, if we know that multiplying fractions tells you, allows you to simply multiply the numerators and multiply the denominators, meters times 1 is going to be meters, seconds times seconds is seconds squared. We get 2 meters over seconds squared. The fourth question asked you a question that was well covered on the document that you were to have done before, on the day, not the days before this test. Okay, and the question asks, explain how average velocity is a rate of change. Explain this in terms of the definition of rate of change. Well, it turns out average velocity is the average rate of change of position with respect to clock time. And that would be change in position divided by change in clock time. That's the definition of average velocity. And of course, we have to apply what we know about the definition of rate of change in order to draw this conclusion. Now, that definition is the average rate of change of A with respect to B is change in A divided by change in B, which we could write as delta A, delta meaning change in, over delta B. It's not A over B. It's change in A divided by change in B. You don't get a rate of anything by dividing A by B. Change in A divided by change in B. Now, here we want the definition of average velocity. That's the average rate of change of position with respect to clock time. You have position before the with respect to, clock time after with respect to x2, with respect to. So the position is your A quantity, and your clock time is your B quantity. Then, since the average rate is change in A divided by change in B, it's change in A, which is change in position, divided by change in clock time, which is change in B, which is change in clock time. You really want to digest this definition of average rate because it occurs so many times during the course, and the way we use it is so similar in those different contexts. So you really want to be sure you understand this and understand how average velocity is a rate of change of position with respect to clock time. And this average rate of change of velocity with respect to clock time is what we call acceleration. And we're going to talk about what good that is and what we can learn by understanding velocity and acceleration and how they're related.